In Chapter 16, we're going to learn how to find double and triple integrals. And we're going to begin with the most basic type of that, which is double integrals over a rectangular region. Now, before we begin all of that, we need to review Calc 1 and talk about how we developed the area under a curve in the first place. So if you remember from Calc 1, you would have a curve, and then you would have a rectangle that has some function value for that curve. So for example, you have the height right here of that rectangle, which is equal to the function value at CI, where CI is the value in the middle, if you will, between your x values. And this distance from one side to the other of that rectangle is your change in x. Okay, so the area of a rectangle, we've learned from basic geometry, is base times height. So if I look at the base of that rectangle, that's change in x. So delta x times the height, which is the function value at CI, with CI being some x value. Okay, so if that's just one rectangle underneath the curve. So if I want the area under the whole curve, what I want to do is I want to stack up all of those rectangles. So I want to find all of the FCI's times delta x's, right? Rectangle, rectangle, more rectangles, and I want to add them all up, right? So the area of each rectangle. And I would start at 1 and I would end at n. Now this is approximate, right? So you'll note. Not exact, right? Because we're stacking up discrete rectangles. And you can see what we're doing down here. So you start, you can imagine just one of these and say, I'm going to find the area of each of these rectangles and add them up. That's what this is saying. But then how many rectangles you fit in is n, right? So over here we have fewer rectangles to more rectangles. And obviously the more rectangles we have, the better the approximation. So this is a weak approximation over here. And then as n increases, right? So this is small n. And over here we have a large n, large number of rectangles. So we have a better approximation. But of course, the best approximation is not an approximation at all. The best approximation would be to let the number of rectangles go to infinity. And if we do that, then we're not looking at an approximation anymore at all. We're finding the exact value. And that's what we learned in Calc 1. If we take the limit as n goes to infinity, so the limit as n goes to infinity of that summation, right, then we've actually found the exact area under that curve. It equals this value. It's not an approximation. It's exact. And of course, we don't notate it this way. We've learned, right? So that what we're really doing is the notation is written as the integral from a to b of f of x, which is our function, dx, right? But when you think about what you're doing here, this is really height, and this is the base of a bunch of little rectangles, imaginary rectangles, if you will, inside this curve, right? Under the curve between whatever values you're looking at. In this case, we're going 0 to 5, but it doesn't have to be. But that area is that integral, right? The integral finds the area between a curve and, in this case, the x-axis, because I have it with x. And in Calc 2, of course, we learn it doesn't always have to be the x-axis. You can do the y-axis. You can do whatever axis you like, right? But the integral will still find that area. Now, this might look familiar to you. This is Riemann sums, if you remember that from Calc 1. Right? When you're adding up the rectangles, that's Riemann sums. When you take the limit of the number of rectangles and let it go to infinity, then you're finding the integral. It's one of the fundamental theorems of calculus. Okay, so that was Calc 1. But now we want to kick it up a bit and add in another dimension. So we're going to look at this picture. And so what you want to do is you want to imagine, I sort of imagine pillars inside of a hillside, right? And actually there's real life examples of something that looks like this. It's called the Giant's Causeway. That's actually just one of several examples of this. Let me show you a picture. The Giant's Causeway is particularly famous. This is in Ireland. And you can see that it's a bunch of pillars stacking up to create a hillside. That's exactly what we're trying to do, right? We're going to use a bunch of pillars and stack them up, right? Instead of just rectangles, we will stack columns. Okay, so to do that, of course, a column is a three-dimensional thing, right? So we need the volume of a column as opposed to the area of a rectangle from the previous one, right? So we want the volume of a column. Now, a column will have length times width times height. All right, no problem. So let's look at the lengths and the widths, shall we? So the length would be the change in x. So you can see right over here, that piece is the change in x, right? That distance right there. That's change in x. And then change in y would be right here. So that would be back here, change in y. Okay, so change in x times change in y times, all right, what about the height? Well, this particular picture was stolen from some textbook somewhere. And it has KK, which sort of implies that they're always the same, which they are not. So I'm actually going to change this to I and J because they do not have to be the same. They can be different indices. So what this will be is the function value at that particular XY combination. So it'll be, your height will be f of xi, yi, or yj, sorry, yj. Again, they don't have to be the same. All right, so just like with our two-dimensional example, right, we have a basic geometry understanding of one item, and then we're going to stack a whole bunch of them in there, right? Okay, so how do we do that? So the volume under the surface now, right, this isn't really a curve, it's a surface, a hillside, if you will. So the volume under that hillside is approximately, right, we're not finding exactly, and then we have to add up. So we're going to take our function and we're going to add from I equals 1 to n for the change in x. So we're going to add up all the x direction, and then we're also going to add up all the y direction. So from j equals 1 to n, delta y. So we have two addings to do instead of just one, because of course we have more dimensions, right? We have an x dimension and a y dimension, and we need to stack them up. And as before, we can see that if we let the number of columns increase, our curve will get more accurate, right? So this has a low n, so it's not a good approximation. So poor approximation. If I can fit the word approximation in there. And over here, we have a high number of n. And so we have a good approximation, or a better approximation. The larger your n, the better your approximation will be. Until, of course, you take the limit. Right? Just as with a two-dimensional item, with three dimensions, it works the same way. So the volume under the surface is, right, equals exactly the limit as n goes to infinity of the summations from j equals 1 to n, I equals 1 to n, f of x, I, y, j, delta x, delta y. This is exact. It's that fundamental theorem of calculus we learned way back in the day, right? So how would that work? Well, the integral, you'd have two integrals, right? We don't usually write it this way, of course. We write it with the integral sign. So the integral is saying, hey, take your function and integrate it with respect to x and then respect to y. X will have particular values. So you put x on the inside, and so that goes with this symbol here. It's like they're nested. So you'll say x goes from A to B. So those ones go together. Whereas B is here and A is, back there somewhere in the x direction. And then your y value will go from C to D, where D is over here and C is somewhere back there. And that integration goes with that symbol. So as you can see, so far this isn't really that much different than what we did in Calc 1, right? It's just you're doing it in a third dimension, so you have more things to stack up. So you're going to add not rectangles like we did in Calc 1, right, with the Riemann sums, but we're going to add vertical columns up. We're going to stack these vertical columns together, and we're going to put more and more and more and more of them, infinitely many of them in, and that will give us the volume under that surface.